The following is part 2 of Aircraft Fuel Metering Systems, a specialized maintenance training program designed to help you, the aviation technician, learn more about these important power plant components. In this portion, we will discuss pressure carburetors and 2 of the more popular fuel injection systems used on our modern aircraft. In part 1, we learned how a fuel metering system measures the amount of air entering the engine and how fuel is metered into this air needed to produce power. Also, we discovered how a mixture control is used to maintain the mixture ratio as the air density changes, and that there must be some provision for enriching the mixture under conditions of full power to remove some of the excess heat from the cylinder heads. Pressure carburetors and fuel injection systems perform these same functions in a little different way. In addition, they are less susceptible to the formation of carburetor ice than float carburetors, as well as distribute a more uniform fuel and air mixture than simple fuel metering systems. To begin with, a pressure carburetor is a closed fuel metering system with no point open to the atmosphere between the tank and the discharge nozzle. Fuel is drawn from the tank, pressurized by a pump, metered by the carburetor, and sprayed into the induction air. Any vapors which interfere with metering are returned to the tank from the carburetor. In this unit, the main metering system balances fuel and air forces to produce a fuel pressure that will push just the correct amount of fuel through a fixed metering jet. A special venturi is mounted on the engine in such a way that all of the air entering the cylinders must flow through it. At its narrowest point, the air pressure is lowest, and this low pressure, which varies with the velocity of the air, is directed into one of the regulator compartments. Here, this air meets with impact air pressure coming from around the inlet of the carburetor, which is directed to the opposite side of the air diaphragm. These 2 pressures, the venturi pressure and the impact pressure, both act on a diaphragm to cause it to open a poppet valve. At the same time, fuel flowing through the poppet valve presses on a fuel diaphragm attempting to close the poppet valve. In addition, a special constant pressure discharge valve through which the fuel must flow to spray into the airstream is used to maintain a constant pressure against the fuel, regardless of the amount of fuel flowing through it. Now, with a regulated fuel pressure on one side of the fixed metering jet and a constant fuel pressure on the opposite side, the amount of fuel being forced through the jet will be proportional to the amount of air flowing into the engine. In a pressure carburetor, when it becomes necessary to lean the mixture, the manual mixture control is merely pulled out. This pulls out a tapered needle located in a passage between the 2 sides of the air diaphragm, decreasing the pressure difference between the 2 sides, causing the fuel poppet valve to partially close. This lowers the regulated fuel pressure and leans the fuel-air mixture. Some models of pressure carburetors use an automatic mixture control as well as a manual control. This automatic control employs a reverse tapered needle valve operated by an evacuated bellows. As the air density decreases, these bellows expand to force the needle to open the passage between the 2 chambers and automatically maintain the fuel-air mixture ratio set by the pilot. In a pressure carburetor, there is not enough airflow through the carburetor to provide a stable air metering force for idling. So, a heavy coiled spring is installed in the impact air chamber. This spring holds the diaphragm over just enough to allow the poppet valve to open and provide fuel for idling. When the throttle is closed for idling, however, all of the fuel that is discharged must pass through the nearly closed idle valve. This valve is connected by an adjustable linkage to the throttle air valve. So they open and close together. In this type of system, the idling RPM can be adjusted simply by turning the stop screw for the butterfly type air valve. The idle mixture is adjusted by the amount the mixture adjustment holds the idle valve off its seat. In pressure carburetors, when the throttle is suddenly opened from idle to cruise or to full power, there is a momentary hesitation before there is enough air passing through the carburetor to properly meter the fuel. To overcome this hesitation, a diaphragm-type acceleration pump is used to force additional fuel through the discharge nozzle. To understand how this pump works, let's look at what happens when the throttle is closed. Here, very low air pressure on the engine side of the valve pulls the accelerator pump diaphragm over, and metered fuel fills the pump cavity. But when the throttle is opened, the pressure on the engine side of the throttle raises suddenly. And since it can no longer hold the diaphragm over, the fuel is forced out of the pump into the airstream through the main discharge nozzle. After this fuel passes through the discharge valve, air is mixed with it to aid in atomization. From here, it is sprayed into the airstream. The fact that the fuel sprays out under pressure into the relatively warm intake pipes reduces the possibility of carburetor ice, which is a common problem in float carburetors. Now, let's see what happens in pressure carburetors during full power operation. This is when additional fuel must be automatically metered into the air. Bendix's pressure carburetors use either of two methods to perform this function. The first is an airflow type enrichment system, which has a diaphragm-operated needle valve located parallel to the main metering jet. Here, metered fuel under pressure acts on one side of the diaphragm, and Venturi air under pressure is on the other side. When there is sufficient airflow through the engine to demand additional fuel, both the metered fuel pressure and the Venturi pressure will be sufficient to open the valve. This allows additional fuel to flow from the regulated fuel pressure chamber to the discharge nozzle. The second type of metering is a manual power enrichment system. This uses a step-cut idle valve. When the throttle is in the idle position, this valve is almost closed by the larger taper on the needle. During cruise, the cruise step of the needle restricts the flow. But for full power, this needle is completely withdrawn from the orifice, creating an opening larger than the main metering jet, which will do the actual metering. As you can see, the pressure carburetor overcomes many of the limitations of the more simple float carburetor. It is not affected by the attitude of the aircraft, and it is not susceptible to the formation of carburetor ice. Pressure carburetors still have their problems, though, because their fuel is injected into the airstream at the beginning of the induction system. This causes a non-uniform mixture between the cylinders, a condition that is cured to a large extent by the use of fuel injection systems. At this point, let's examine the fuel injection systems used by our modern aircraft engines. These systems are usually a constant flow type. quite unlike the high-pressure direct injection systems used by diesel engines or even those used on some large radial engines during World War II. These modern systems are very similar in operation to a pressure carburetor because the air entering the engine is measured and fuel under pressure is regulated proportional to this mass of air. This regulated fuel is then metered and distributed to the individual cylinders where it is discharged from the nozzle in a constant flow, just outside the intake valve of the cylinder. The air metering force is composed of impact air pressure obtained from tubes sticking into the airstream in front of the venturi, as well as venturi pressure taken from the most narrow part of the venturi tube through which all of the air entering the engine must flow. The actual fuel metering force is comprised of engine pump fuel pressure acting on one side of the fuel diaphragm and metered fuel pressure on the opposite side. This arrangement helps balance out any fluctuation in the engine pump pressure, making this pressure less critical. The throttle fuel valve is a variable orifice located in series with the regulator and the engine. It is connected by a rigid linkage to the throttle air valve, so that when one is opened, the other is opened proportionately. In a fuel injection system, the mixture control is simply another variable orifice, connected in series with the throttle fuel valve. This orifice is controlled from the cockpit by the pilot and restricts the flow without having any effect on the airflow. To shut off the engine, the mixture control orifice is merely closed, which stops the fuel flow to the engine. The main metering jet in a fuel injection system is a fixed orifice located between the throttle valve and the mixture control. When the throttle is wide open and the mixture control in full rich position, the main metering orifice restricts the amount of fuel that can flow. The balance between the air metering force and the fuel metering force is important because they determine the position of a special ball valve in the regulator. The position of this valve controls the amount of fuel pressure on the discharge side of the metering orifices. This, as you remember, is exactly opposite of pressure carburetors, which holds downstream pressure constant and vary the pressure before the metering jet. In a fuel injection system during idling, there is insufficient airflow for the regulator to be effective. Therefore, a constant head spring holds the ball valve slightly off of its seat. This provides the proper fuel pressure for idling. At the same time, the position of the throttle fuel valve determines the amount of fuel that can flow under this pressure. The throttle air valve stop is designed to limit the amount of air flowing into the engine. This slows the engine RPM to idle. At the same time, the length of the connector between the air valve and the fuel valve controls the amount of fuel that can flow, providing the proper mixture for idling. Some models of Bendix fuel injection systems employ a special power enrichment system. This consists of a main metering orifice located in parallel with the power enrichment orifice, which is uncovered when the throttle is wide open. When the throttle is brought back to cruise position, however, the power enrichment orifice is closed. Now that we understand how fuel is metered in a fuel injection system, let's follow the fuel as it leaves the regulator. At this point, it flows through a flexible line to a flow divider or distributor valve mounted on top of the engine near its center. This divider valve does two things. It distributes metered fuel to the cylinders and provides a positive shutoff for the fuel when the mixture control is placed in the idle cutoff position. These stainless steel lines of nearly the same length connect the distributor valve to the individual injection nozzles installed on the cylinder. The nozzles used in a continuous flow fuel injection system are the air bleed type. Now, this means the fuel flows from the distributor valve in a continuous flow and passes through a metering orifice in the nozzle. When the intake valve opens, the low pressure pulls the fuel into the cylinder. At the same time, it causes air to be drawn into the nozzle through the air bleed hole, emulsifying the fuel as it enters the cylinder. This ensures complete vaporization of the fuel before it enters the combustion chamber. To measure the fuel pressure across these discharge nozzles, a pressure gauge is connected to the distributor valve. And since the flow through a fixed orifice is a direct function of the pressure across the orifice, these gauges are calibrated in terms of flow. Because of the type of flow measurement used in a continuous flow fuel injection system, the aviation technician must be aware of the fact that a clogged injector nozzle, while decreasing the amount of fuel flow, will actually show an increased indication on the flow meter. Just the opposite of what is really happening. Today's turbocharged engines, because of their high power output and efficiency, almost always use fuel injection systems to perform fuel metering. And because these engines often have manifold pressures higher than the ambient air pressure, special provisions must be made to keep the fuel from being blown out of the nozzle through the air bleed hole. To prevent this, these nozzles are usually shrouded, with the shroud connected to the turbocharger discharge pressure. The fuel flow meter used by turbocharged engines is different from meters used on normally aspirated engines. This is because turbocharged engines require a differential pressure gauge to measure the difference in pressure between the metered fuel and discharge air pressure. The main benefit of fuel injection systems over carburetors is that they provide a uniform mixture distribution. The Bendix fuel injection system we have just discussed uses both the velocity of the air and its ram pressure to establish a fuel metering force. In comparison, the Teledyne Continental fuel injection system accomplishes the same end result as the Bendix system, but uses an entirely different principle. The heart of the Teledyne Continental system is a special engine-driven, vane-type, constant displacement fuel pump. This pump is equipped with an orifice and a relief valve to provide a controlled fuel pressure proportional to the engine RPM. This positive displacement pump moves a given amount of fuel with each revolution, and if its output is restricted in any way, a pressure will build up proportional to its speed. Basically, this is what we want to do, but at this point we have almost no control over the actual amount of fuel being delivered to the engine, because this depends entirely on the amount of restriction provided by the injector nozzles. By installing a restricting orifice in a return line between the pump outlet and inlet, we can control the amount of fuel delivered to the engine, and the pressure of this fuel can be made to vary with the speed of the pump. This means when the orifice is large, the pump discharge pressure will be low, and when it is small, the pump discharge pressure will be high, but it will vary as the pump speed changes. The orifice installed in the bypass line around the pump is an effective way of producing a fuel pressure that varies with the engine speed, but it has one serious drawback. During low RPM conditions, it is ineffective because most of the fuel will bypass rather than go to the engine. To overcome this difficulty in the Teledyne Continental system, a relief valve is installed in series with the orifice. And during low RPM, this relief valve holds a calibrated force against the bypass fuel, producing accurately controlled pressure in the system for idling. When the pump RPM increases, this pressure is high enough to hold the relief valve fully off its seat, allowing the orifice to control fuel flow. A bypass check valve in the pump allows fuel under pressure from the aircraft boost pump to flow straight through to the cylinders for starting. But when the pump outlet pressure is higher than that of the boost pump, this check valve will automatically close. Another interesting feature of this system is that fuel entering the pump from the aircraft fuel system is swirled to separate the vapors from the liquid fuel. And a small amount of fuel from the discharge side of the pump passes through a Venturi-type vapor ejector. This ejector picks up vapors released from the fuel and carries them back to the tank. So now, vapor-free fuel with a pressure proportional to the engine RPM is delivered to the fuel control unit. This fuel first passes through a mixture control. This is a variable selector valve, which in the full rich position passes all of the fuel to the throttle. In the cutoff position, however, this fuel is routed back to the inlet side of the pump. At any position between cutoff and full rich, some of the fuel returns to the pump and some of it goes to the throttle. The throttle fuel valve used in this system is merely a variable orifice located between the mixture control and the engine. It is connected by a linkage to the throttle air valve. So, as the throttle control in the cockpit is moved, the amount of both air and fuel directed into the engine is varied. As with all of the types of pressure fuel metering systems we have discussed, controlling the closed position of the throttle air valve determines the idling RPM of the engine. And by varying the length of the connecting rod between the throttle air and fuel valves, we can control fuel flow at idle, which controls idle mixture and smoothness of engine operation. The manifold valve used by the Teledyne Continental fuel injection systems not only provides uniform distribution of the fuel to the cylinders, but assures a positive shutoff of the fuel when the mixture control is placed in the cutoff position. It also incorporates a poppet valve that prevents fuel flowing to the nozzles until sufficient pressure has been built up in the valve. This assures that it is fully open and will do no metering. From this point, we can see that uniform lengths of stainless steel tubing are used to connect the manifold valve with the individual nozzles installed on each cylinder. And each nozzle has a very accurately calibrated orifice through which the fuel delivered by the distributor valve must pass. There are several orifice sizes used in these nozzles. Their flow range is identified by a letter stamped on the side of the nozzle. The lower the letter in the alphabet, the more fuel will be passed by the nozzle for a given pressure. An air bleed hole is also incorporated into each injector nozzle to help atomize the fuel as it is sprayed into the intake valve chamber. Turbocharged engines use the same type of injector nozzles as normally aspirated engines, except the shroud that encloses the nozzle is connected to the turbocharger discharge, or as it is properly called, the upper deck pressure. The fuel flow meter used on Teledyne Continental turbocharged engines is also a differential pressure gauge. This gauge reads the difference between the fuel pressure at the discharge nozzle and the upper deck pressure. But the greatest difference between a fuel injection system for a turbocharged engine and one for a normally aspirated engine lies in the injector pump itself. The orifice in the pump for a turbocharged engine is variable and is controlled with an aneroid, or an evacuated bellows system that senses upper deck pressure. For example, if a pump with a fixed orifice were used in a turbocharged system and the throttle opened suddenly, the engine would accelerate, with the fuel pressure going up before the turbocharger has time to spin up and increase air density proportionally. This will cause the engine to hesitate because of the excessive rich mixture. In comparison, if the orifice is controlled by an aneroid and the throttle is suddenly opened, the upper deck pressure will drop. This causes the aneroid to increase the orifice size, which decreases fuel pressure to the nozzles until the turbocharger increases the upper deck pressure. At this point, the aneroid will decrease the size of the orifice and increase the amount of fuel supplied to the nozzles. Servicing Teledyne Continental fuel injection systems must be done in strict accordance with the recommendations of the manufacturer, and its troubleshooting is quite straightforward. Perhaps the most common trouble with any fuel injection system is a plugged nozzle. If there is trouble with uneven running, check to be sure that all of the nozzles flow a uniform amount of fuel. Clean the nozzles by soaking them in acetone or MEK and flow them out in the direction opposite normal flow. Examine them with a light to be sure that there is no obstruction in the passages. With all of the nozzles clean and properly installed, connect an accurate pressure gauge in a T-fitting between the fuel control and the manifold valve. And with the engine running at a low speed recommended in the service instructions, check the low unmetered fuel pressure. It must be with the tolerance specified by the manufacturer. If it is not, improper low unmetered fuel pressure can be adjusted with the relief valve. Now, operate the engine at the speed recommended to check the high unmetered pressure with a test gauge. It must be within the range recommended by the manufacturer. If it is not, it can be adjusted by changing the size of the orifice. Be very careful when checking the high unmetered fuel pressure Only run the engine at this high power setting for a very short period of time, because the engine can be damaged from prolonged high power output on the ground with inadequate cooling. Adjust the idling RPM by setting the throttle stop, and check the idling mixture by slowly pulling the mixture control into the idle cutoff position. There should be a slight rise in RPM before the engine stops entirely. After the system is checked for the proper unmetered fuel pressure and for the proper idling RPM and mixture, it must be test flown to check metered fuel pressure against the specifications established by the manufacturer. Pressure carburetors and fuel injection systems are intolerant of improper servicing. They are precision components and require sophisticated flow benches to calibrate them. While the aviation technician is restricted in the major overhaul and calibration of these critical systems, he is charged with the responsibility of servicing and maintaining them at their peak performance. Fuel metering systems are blamed for many faults for which they are not responsible. So before performing any maintenance on pressure carburetors or fuel injection systems, be sure that both ignition systems are operating properly. All of the fuel strainers are clean, and the selector valves allow maximum fuel flow. The air filters must be clean, and the muffler must not be causing any undue back pressure. The turbocharger must be operating properly, and there must be no leaks in the induction system. The propeller governor must be properly adjusted, and the tachometer must be accurate. Finally, the accuracy of the fuel flow meter, which is actually the metered fuel pressure gauge, should be checked, because trying to calibrate a fuel injection system with inaccurate instruments can lead only to frustration. Be sure that all calibration and servicing is done in accordance with the latest service bulletins and manufacturer's service information. Finally, if the recommended troubleshooting and servicing does not restore the performance of the engine, the entire fuel injection system should be returned to the manufacturer or to one of his approved service stations for complete overhaul and calibration. The purpose of this training series is to promote safety through education. And it is with gratitude that we acknowledge those who have helped in the production of this program.